Hi, in this video I'm going to give you a quick breakdown on the different extraction tools in base R. Now for the record, there are a lot of other options, but these are the ones that work throughout pretty much all R packages and frequently are the only tools available in many of the bioinformatics packages that you might encounter. Now, if you are coming from the data science world, there is a whole universe, a tidyverse, if you will, of packages meant to help make this process a little bit more understandable. But in my class, I like to use these base R tools because they make you think about what's going on the data side of things. So I'm going to collapse this, not a very long script file, but I do have a table of contents here. We're going to start off making a few different objects, vec1, mat1, df1, just printing off what those look like. Go away. If I print off vec1, there it is. mat1, there it is. df1, similar, but it's got different columns. Each column is a different type of data, so numeric, character, and character. Here we have a character vector, and here we have a character matrix. Remembering that a matrix is basically just a fancy vector where it has attributes describing rows and columns, and the class matrix and array that allow R to print it as a data frame, or sorry, as a rectangle, as a matrix. A vector is a very simple type of data, in this case a character vector, but then a data frame is actually list type. That's list type. That's what allows it to have these different columns, each with different properties. That matters because the first two tools are really my favorite, specifically the $sign, but they only work on data frames and list type data in more general terms. The first one is the double square bracket tool. It looks like the single square bracket tool. It works completely differently. It's almost wholly analogous, though, to the $sign. And that's because they both open up the contents of the indicated container. So for example, here I am opening up container 2. I could also have named it. So I could have said upper. Either one is going to work, but notice it gets the contents of those containers, which are vectors. It's no longer printing off in this data frame fashion because it's no longer a data frame. If I really wanted to prove it to myself, I could check the class, and I'm going to see that the class is character because it's now a very simple character type data. And because it doesn't have any other properties, that class is the same name, so just character. The $sign is my favorite because of this property right here. If I type in the name of the list type data and then $sign, the pop-up allows me to choose, and then there's even like a little preview of what's in there between the different columns. I'm going to press tab again, and it's auto-completed, and I can run it. So note, the operation, though, is precisely the same. It returns the contents of the container. This is my go-to method. Most of my data is organized into data frames, and so this is usually working because data frames always have container names. It's just a property of data frames. You could put quotes on it, and sometimes that's needed if for somehow you manage to get a data frame with like spaces and stuff inside of it. But most of the time I will use it unquoted. In the end, though, the pop-up menu helps you select by name. So that brings us to the actual reason for this video, because if that's as hard as it was, that wouldn't be a whole video in itself. But the square bracket tool actually takes a little bit more explaining. So for that, I need a little bit more room on my screen. So on this first example, we can see that the data to the left is one-dimensional. That means that the argument that goes inside of the single square brackets needs to only have one argument. So right now, I had a typo. Once I had that vec1, I'm extracting positions 2, 3, and 4 because that's what this resolves to. So that is a one-dimensional extraction using a length 3 integer vector. It's integer because that's what colon produces. You're going to see me be specific because I don't want to be wrong, but I don't normally really care as long as it was a integer or even numeric without some decimal places, it's going to extract the corresponding positions. I believe if you did give it a decimal value, it floors the value if memory serves, but I'd have to check that out to be sure. So the main thing with the square bracket tool is that if the data to the left is two-dimensional, you usually want to be using two arguments. And that means that sometimes you're going to leave an argument blank in order to not reduce it. In other words, to return all the values. So this first example is rows 1 and 2 using a length 2 integer vector, and then all columns because I left it blank. And there you go, rows 1 and 2, row 1 and 2, 1 and 2, all columns. Here though, I've specified the value in both the row and the columns, and I do want you to note that this returns a single value, and this single value is actually a vector. This comes to this concept of simplifying. Whenever we simplify to a single column, it simplifies to a vector, at least by default. There are ways to turn that off. There's an argument that you can add to the square bracket tool. You'd have to name it though. It's like .simplify or something like that. You can look up in the help file. But by default, R will simplify a extraction resulting in one column from a data frame to a vector. It's a quirk. You kind of have to memorize it and just incorporate it into how you think about this. So for example, right here, I am extracting all rows across column 1, so that's a length 1 numeric vector. But that output, which also happens to be, I think that's an integer vector if memory serves. Let's see. It is a length 10 integer vector. But that's because it reduced to a single column, and that's just what R does. The opposite's not true. If I have multiple columns across a single row, that remains as a data frame. Anytime you have multiple columns of a data frame, that will remain a data frame. And the reason why is because those are separate containers in memory, and R just doesn't feel safe simplifying them to a single type of data, whereas because the contents of a data frame, single column has to be a single type of data, it does feel comfortable making that simplification, at least by default. The other caveat here is, yes, I've already said that we have to choose the right tool based on the dimensionality. However, as long as you are extracting from two-dimensional data, you can use one argument. Just weird stuff starts to happen, and I generally recommend that you avoid it. So for example, here, no comma in here means that I am extracting using a one-dimensional method from a data frame. And what that results in is treating it as if it's a list class object and simply pulling out that second container, because that's kind of like the 1D view of list data is as a series of containers, a vector of containers. And that's what I'm doing this extraction of. Now, please note, it's the container itself. This still has column and row names because it is still a data frame. It's just now a one column data frame, one column and 10 rows. This is not true with a matrix, but a matrix also gets weirdly treated. The main thing here is that it is going to go through and it's going to snake across. I'm actually going to change this value to 7. It is going to go 1, 2, 3, 4, 5, 6, and 7. So it's going to end up returning position G. And that's just because in memory, a matrix is stored as a vector. When trying to extract from this two-dimensional object using one-dimensional methods, R has to figure out how to treat it, and that's how it does. That's how it's stored in memory, actually. First rows, then columns. If the data to the left is 1D and you use 2 arguments, which is the most common error many of you will see, you get something like incorrect number of dimensions. Sometimes it's slightly different, but oftentimes this is the main cause, especially whenever you mention dimensions. It's trying to extract from a vector using two-dimensional methods. This is most common when you're starting to string things together. So for example, if I start with my data frame and then I'm actually wanting to extract like B and C, I could string them together. I could say first extract from a data frame, then from that resulting vector, extract 2 through 3. And when I do that, it works. But what students will do is they'll be like, all right, I want rows 2 through 3, and then they'll put a comma, and you get a message like this because, well, you're trying to extract from this as if it has rows 2 and 3. But at that point, after the $ has happened, it no longer has rows 2 and 3. Common issue. The other thing with the square bracket tool is not only does it allow you to work with different shapes of data and even treat the same shape of data in different ways depending on how you use it, it also allows you to use different types of inputs for the arguments that you're using. So we've already seen lots of examples of position-based extractions. So here, one-dimensional extraction. Note there's no comma in here. This right here is a length 5 integer vector. So that's going to extract positions 2, 3, 4, 5, and 6 from vec1. So about what you'd expect. This just is a common thing people get confused by. The difference between C and colon is C just combines values. It's a handy tool for combining different values into a single object. Colon makes an object based on an analysis of the values to the left and to the right and all the values in between. So 2 through 6, literally 2 and 6. But this is going to return just position 2 and 6. Not too bad. This one is going to do a two-dimensional extraction. It is going to get row 1 across columns 1 through 2, which looks like that. Note that is still a data frame because of what I said earlier. If you do not simplify to a single column, R does not take it upon itself to simplify. Even if it's a single row, it only works if it's a single column. So for example, here, all rows across column 2 is a single column, and so it simplifies it to the type of data inside that column, which is a character vector. Down here, we have the examples of character names for those position names. So this only works if the data has position names. So for example, a data frame always has column names and it has row names. Although here our row names are very simple. They're simply the number of the row. So I could, if I wanted to, I could have a symbol here saying that I want row 2 and column lower, and it doesn't have an issue, but that's somewhat unusual. I would probably have normally just said 2, and that gives me the same value because the character and the position are the same. That's not true with the column name. I couldn't have said quotation mark 2 instead of lower because quotation mark 2 isn't the name of one of the columns. Instead, the name is lower. Please note, unlike the $, this does require quotation marks because, well, that's actually a special property of $. Most of the time when referring to the names of columns in R, you're referring to character values that are stored alongside the data in a thing called the attributes, the column names specifically, or dim names. But these column names are stored in memory as a character value, and most of the time that's how we reference them. On the other hand, the $, as well as like ggplot2 and a number of other tools actually allow us to use unquoted column names, but let's not do that now. Here's another example of using column names, using a character value. This time though, because it's not going to return a single column, it is going to return a data frame. In this case, a data frame consisting of all rows, since that was left blank, across columns lower and upper. Now, what's nice about this character value is it means that it returns an error if you have a typo, which oftentimes is a big problem, and you want to return a error message. What you don't want is to be extracting by position, but somebody having rearranged things on accident, and all of a sudden you're using the wrong data. So character value is often a much safer alternative to the position, since the positions often change, but the column names are typically meaningful. So it's just more of a strategy. And finally, I get to one of my most common tools, which is logic. So logic requires you to usually do some sort of analysis. Here, I first extract the column num, that's returning an integer vector. I'm then comparing that integer vector to the value 3, that's returning logic. That logic is then being used in the row section of my extraction tool. Because I base this logic off of the object I'm extracting from, it all lines up that this first false corresponds to position 1, which corresponds originally to the value in position in row 1 across that column. It all makes sense. In other words, it all lines up. So the trues will correspond to positions that will be extracted. The falses correspond to positions that will not be. Same here. I first pull out the column names. This returned a character vector. I then compare that character vector to the value lower, producing logic false, true, false. So that's a link 3 logic being applied to the columns. And so that works. The main thing is that the logic should correspond to each position. I think something I'd like to add to this is that the length of logic should typically equal the length of the dimension. And I'm such a bad typist. Why do I keep typing 2 L's today? But that's the idea. First logic should match the length of the dimension. So this was length 10 because that's how, or length, 10 because that's how many rows there were. This is length 3 because that's how many columns there were. Like more conceptually, it's because I based it on an analysis of the object itself. But it's just all got to line up. That's the important part. Here I do a fancy one where I first extract the numbers. I then divide by 3 and return the remainder. So 1 divided by 3 returns the value 1. 2 divided by 3 returns the value 2. 3 divided by 3 does not have a remainder, and it returns 0. 4 divided by 3 returns a remainder of 1. 5 divided by 3 returns a remainder of 2. But 6 divided by 3 does not have a remainder. It divides cleanly, and so it returns 0. This repeats, 9. And then if I kept going, it would eventually have been 12, and then 15, and so on, the multiples of 3 dividing cleanly by 3 and returning 0. This allows me to generate some easy logic of every third value being true. I actually use this little line of code all the time because it allows me to very quickly see like a subset of all the data, and I can scan through and check for problems. It's a common tool that I use just when I'm trying to, kind of explore different pieces of a very large object. So maybe I'll do like divide by 1,000,000. And if it's 0, then print off the value. That way I can see every 1,000,000 rows, which is a lot nicer than having to scroll through literally millions of different extractions in order to like see the different pieces of data. Okay, that is my short review of extraction. We're at 20 minutes, so I'm going to stop here. I hope that helped. This is a tool that is used all throughout R, and it's pretty consistent rules. The main thing really is up here though. These two tools only work for list type data, which is lovely and wonderful, but only list type data. The square bracket tool, very flexible based on the structure of the object itself in terms of how many arguments you can use. Finally, this very confusing behavior of it simplifying whenever extracting down to a single column of a data frame. There's other simplification complications, such as when extracting from a matrix, But in the end, you learn a lot of these subtleties through experience and practice. As long as you're visualizing your results and coming to understand the nuances of things through that practice, you're learning and you're doing great. So good luck and see you next time.